Notice, and this is the typical copyright. We continue with mathematics syllabus for CSEC, which became effective in 2018. As of January 2026, this syllabus has not been revised, but there are plans to change the structure of the exam from 2028 and onwards, with a few pilot projects now being conducted in a few Caribbean countries. The syllabus itself remains unchanged. The main planned change to the CSEC level math exam is to split the exam into two parts. This is the 13th of 24 videos. I will have to readjust the schedule. We have completed Objective 5 in 4 parts. We are now at Objective 6, which covers this whole page. We will try to do everything in one video. So we have finished up to here. So far in this section, those 3 have been published in their entirety, the others partially published. We are now here, Objective 6 in Section 8. This is video 13. When it is finished, it will be published in its entirety. And for the rest of the videos in this section, these other 4 will be published in their entirety when I finish with them, and of course, the others partially. So we are here, Objective 6. It says solve geometric problems using properties of circles and circle theorems. So we will have to learn about the anatomy of the circle, and then we will learn about the circle theorems, 9 of them, and then solve some simple problems using those circle theorems. So that is what we'll be doing. It will be a long video, since we have to look at 9 circle theorems that CSEC has listed in the syllabus. Now, circle theorems, here you have the first 5. We will look at them in detail as we go along later on. And then you have another 4, 9 circle theorems. So we will begin with introduction and terminology, and then we will look at the circle theorems, then we will review, and then we will look at some practice questions. So what is a circle? If you were told in school to draw a circle, you would draw something like this using your pair of compasses, and you end up with something like this. Now the question is, what really is a circle? Is it this red line out here? Or is it the space in here? So this dictionary here says it is the shape. It is a space within that red line. This other dictionary here says it is a round plane figure. So it is saying it is a space. This next one here says it is a round shape. So it is a space. And lastly, this dictionary here says it is a shape. So again, those 4 dictionaries say it is the space within that red line. However, your syllabus says, and this is a definition from your syllabus, that a circle is the set of points in a plane that are all at a fixed distance from a given point that is called the center. So according to this definition in your syllabus, it is not the space in there, it is actually this red line here. And this other dictionary here, it begins by saying it is the curved line, and then it says it is the surface bounded. So you have 2 definitions here for a circle. This next dictionary here says it is the curved lines, and then it also says, or the area enclosed by such a line. So it is saying, first of all, it is the line, or it is the space in here. And this last dictionary down here, this dictionary here, says A, it is a plane curve, so it is saying it is a red line. And then B, it is a planar region bounded by a circle. So here it is saying it is a red line, and now it is saying it is a region within the red line. So your syllabus says it is the red line. It is a set of points in a plane. Now Wikipedia summarizes it this way. It is a closed shape, so that is the space in between, and then it says it is a curve. Now in strict technical usage, the circle is only the boundary, that is to say, it is only the red line, as your syllabus here says. And the whole figure is called the disk. So what is a circle? According to your syllabus here, it is that red line, this red line. The distance around the red line is called the circumference, but sometimes it is used interchangeably for the circle, which is a red line. If you draw a line from the center to the circumference, you have a radius, you draw another radius, the space between here is called a sector. And if you draw a line from one part of the circumference to another, that line is called a chord. This part of the circle is called an arc. The space between that arc and that chord is called a segment. Now, this is from your syllabus. It says that a segment of a circle is a closed figure formed by an arc and a chord. So according to this part of the syllabus, it is now saying inside here is part of the circle. And then you would read something like this. Calculate the area of polygons and circles. How do you calculate the area of a circle if the circle is a red line? You can only calculate the area of the circle if the circle is the space in here. So your syllabus is inconsistent. At one time, it defines the circle as the red line, and other places it will tell you to find the area of a circle. So what is our conclusion? Technically, the circle is the curved line as defined here. We will accept that definition. However, in normal usage every day, it is also the space so enclosed. So when you hear about a circle, it may mean the red line, or it may mean the space in between here, depending on the context. Okay, so now that we know what a circle is and what it looks like, let's learn about the anatomy of a circle. Well, we know what the center is. If we don't, here is the definition. Center of a circle is the point inside the circle from which all points on the circle are the same distance if the circle is defined as the curved line. Or the center of a circle is the point on the circle from which all points along its boundary are the same distance if the circle is defined as the area enclosed by the curved line. So that's the center. What is a radius? The radius of a circle, which could also mean the length of that line, from the center to any point on its edge. That's a radius. What's the circumference? The circumference of a circle is the distance along the circle. Now here the circle actually means the red line. It's a special name for the perimeter of the circle. And now circle here means the space inside. So it is used interchangeably. In normal usage, the circumference is the curved line demarcating the boundary of the circle. So we talked about those three already. Now what is a chord? A chord is the line that connects any 2 points on the circle or the circumference. That there is a chord. What is the diameter? The diameter of a circle is a special chord that passes through the center of the circle. This is from the syllabus. So if we draw a chord like that, joining those 2 parts of the circle, and it passes through the center, that chord is called a diameter. What is an arc? An arc is a portion of a circle, also a portion of any curve. That is from your syllabus. So this part from here, going like that and coming back here, that part there is an arc. But of course, so is the other part on this side. That is also an arc. What is a segment? A segment of a circle is a closed figure formed by an arc and a chord. That's a definition from the syllabus. So you have an arc here. You have a chord here. This space here is a segment of the circle. Now we are defining the circle as a space within that red line. What is a sector? A sector of a circle is the closed figure formed by an arc and 2 radii of the circle. So you have a radius here. You have another radius here. You have an arc here. This space here is a sector. What is a tangent? A line is a tangent to a curve at a point A if it just touches the curve at A in such a way that it remains on one side of the curve at A. A tangent to a circle intersects the circle only once. That is from the syllabus. So you have a line like this. That's the tangent. It touches the circle only once. What is a semicircle? Well, semi actually means half. So a semicircle really means half of a circle. However, we have a little more sophisticated definition here. A semicircle is a segment whose chord is the diameter. In this case, the semicircle segment and the semicircle sector are the same. So remember, this diameter is a chord. That up there is an arc. This space in here is a segment. It is a segment. However, because this diameter is actually 2 radii, one that way and one that way, then this part of the circle here is enclosed by an arc and 2 radii. So it is also a sector. Each half is a segment as well as a sector. Segment down here, sector down here as well. Now, one more thing we need to talk about here, pi. Now, the Greek letter, which is written this way, we call it pi, is a mathematical constant designating the ratio of the circumference of a circle to its diameter. Its approximate value is 3.143, or sometimes for convenience you may see it as 22/7. So it's the ratio of the circumference to the diameter, or you could write it as C/D, which is 22/7. For the area of a circle, you may have seen area of a circle is equal to pi r squared. That is this number here, that 22/7. If you start out from this left side of that diameter and you walk straight across, it is 7 meters long, 7 meters long. You would have covered, of course, a distance of 7 meters. Now, once you reach here, if you go all the way around like this, along the circumference and back here, you would have covered a distance of 22 meters. And that is how we get 22/7. That ratio holds for any circle. The circumference is 3.143 times longer. Okay, so now that we know about the anatomy of a circle and the terminology, we will deal with the circle theorems. First of all, let's look at these three. They are fairly simple. The first one says, the angle which an arc of a circle subtends at the center of a circle is twice the angle it subtends at the point of the remaining part of the circumference. So if you have an arc here, A, B, and from that you draw an angle here to the center, and then you take another point over here from the rest of the circumference, and you draw two lines from A and B like that. This one at the center is twice that one on the remaining part of the circumference. Or the one at the circumference is half of the one at the center. This applies to all points along that circumference. Angle C is equal to 2 times angle D, and then we will put in an E and an F just now. That is to say, if C is 100 degrees, then D is 50 degrees. 50 degrees. If you take another point E here, and you draw two more lines from this same arc, then this angle here, in relation to the one at C, C is twice that one there. So it will be 2E, or 50 degrees if C is 100. And you take another point here, say F, and you do the same thing. That angle there is half as much as the one in the center, or the one in the center is twice the one on the remaining part of the circumference. Now that applies for the remaining part of the circumference. It does not apply to this Y here. So if you try to draw an angle here, this angle at C is not twice that one there, 2Y. It only applies to angle on the remaining part of the circumference, not this arc here that you are already using, but the rest of the circumference. We can measure it. If we measure that angle at the center there, we get 80 degrees. And if we project an angle at this circumference here, we measure this, we get 40 degrees. So that one was 40 degrees, this one was 80. We take a new angle at the circumference here. That there is 40, as we can see here. And you could do the same thing for this angle out here. So remember, that one was 80, that one is 40, that one is 40. This one will also be 40 here, as you can see here. So 80, 40, 40, 40. The angle which an arc of a circle subtends at the center of a circle is twice the angle it subtends at any point on the remaining part of the circumference. Okay, that's the first one. The second one, angles at the circumference in the same segment of a circle and subtended by the same arc or chord are equal. This is a spin-off from the first one we just looked at. Remember, we said the angle at the center is twice the angle at the circumference at the other part of the circumference, which means that if we ignore the angle at the center, and we can simplify this, and we get angle D is equal to angle E, which is equal to angle F. So now we will forget about this center here. We will forget about the center here. Let's just pick 2 points, A and B. We put a chord in there, and like what we did previously, we get a point D here, and we create an angle here, and another point E here, create another angle there. What this theorem is saying is that those two angles will be equal to one another. And another one here, that will be equal to all of those, which is actually a direct result from the first circle theorem. We can measure them. So this is our arc here. That's the chord. From there, we draw an angle at this point of the circumference. We measure it. It is 40 degrees. It is 40 degrees. That is our arc and chord. Instead of that point, we use this point. We measure this angle here, and we get 40 degrees. So, angles at the circumference in the same segment of a circle and subtended by the same arc or chord are equal. That's the second circle theorem. They're not really that difficult to learn. If you find this video useful and interesting, please like and share. That is, like and share. You may also consider subscribing to this channel. Now we come to the third circle theorem. The angle at the circumference subtended by the diameter is a right angle. So this is the diameter here. If you have any angle on any side of that circumference, it will always be 90 degrees. If you begin from here and there, A and B. If you begin from A and B. So let's choose D here. That angle there is a right angle. Let's choose E here. That angle there is a right angle. Or F, that angle there is a right angle. Or coming down on the other side down here, Y, this angle is a right angle. This is what this circle theorem says. If you use the diameter and you draw any angle to the circumference on any side, those angles will always be right angles. Let's measure this one. This is the diameter. That's the center. This is our right angle. It's 90 degrees, as you can see here. If we take another pointer, instead of that point, let's take this one. We are using the same diameter, AB. Notice 90 degrees. This angle here is 90 degrees. 90 degrees. The angle at the circumference subtended by the diameter is a right angle. So we have looked at those three. We will now look at these two. Remember from that third one, we said that E is equal to Y. This angle here, E, which is 90 degrees, is equal to Y down here, which is 90 degrees. Now, if we remove some of those lines, we notice we have a quadrilateral in here. But the line from this vertex and that vertex passes through the center, so that's the diameter. When that happens, those angles are 90 degrees. So consider the rectangle AEBY, a cyclic quadrilateral. This brings us to the next circle theorem, which says the opposite angles of a cyclic quadrilateral are supplementary. In this case, because AB was a diameter, then this one up here was 90, and this one down here is 90 as well. But if you add the two 90s, you get 180, so they are supplementary. Now, this is a special case. A diameter joins one pair of opposite vertices, so the other two vertices are each 90 degrees. But remember, if you add those two 90 degrees, you will get 180. It is still supplementary. So let's consider that quadrilateral ABCD. A plus D is equal to 180 degrees. This angle here plus that angle, they are opposite angles of a cyclic quadrilateral. They are supplementary. And B plus E, that one up there, and this one down here, they are opposite angles in a cyclic quadrilateral. They are supplementary. So if B is 100 degrees, if B here is 100 degrees, then E would be 180 minus 100. E will be 180 minus 100, which will be 80. And your reason for that is that opposite angles of a cyclic quadrilateral are supplementary. Let's measure them. If we measure that one, now these single arc here do not mean that those two angles are equal. In this case, it means that they are related. So we will measure them. This angle here, if we measure it, it's a little short of 90. And this angle here, if we measure it, it's a little past 90. Let's see that a little closer. Coming from this direction, that is 92. And this one coming from this direction, that's 88. It hasn't reached 90. So we get 92 plus 88 is 180. They are supplementary. Now remember, those two arcs do not mean that they are equal. In this case, it means that they are related, to separate them from these two on this side. So we will measure these two. This one here, it's a little past 80, looks like 83. And this one down here, it's a little past 90, which is 90. Looks like 97. Let's see that closer. That looks like 83. And this one down here looks like 97. So 83 plus 97 is 180. So the opposite angles in a cyclic quadrilateral are supplementary. Next circus theorem. The exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. Is equal to the interior opposite angle. So let's put in that quadrilateral there again. If we extend this side here, we now have an exterior angle here. That angle is equal to the interior opposite angle. Interior opposite angle. That one. This angle is equal to that one. So I just said that this angle is equal to this one. Let's measure them. This angle here, $70, it hasn't reached 80 as yet. Looks like 75. And this angle over here, 70, it hasn't reached 80, looks like 75. Let's see that closer. 70, we were coming from this side, 75. This one here, we were coming from this side, 75. Now in this case, this single arc here and this single arc here means that those two angles are equal. And that double arc there and this double arc here means that they are equal in this case. So now we measure in here and out there. We got that, which is like 105. And coming from this direction, that looks like 105. So we were coming from that direction, 105. And in this case, we were coming from this direction, 105. So this double arc here and this double arc here, in this case, it means they are equal to each other. And this single arc here and that single arc there means that those angles are equal to each other. So the exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. So we just did that. So as of now, we have completed those 5-circle theorem. Let's look at these two. The angle between a tangent to a circle and a chord through the point of contact is equal to the angle in the alternate segment. Now, this is about the hardest one out of the 9. So let us say you have a tangent here, as you can see. It touches that circle at Q, and we are considering the chord QY, this chord here. The angle between the tangent to a circle and a chord through the point of contact. So this angle here, we will consider this angle here for now, is equal to the angle in the alternate segment. That is to say, this other segment over here. Remember this segment here. If we draw an angle at this point, this angle is equal to that angle. So let's measure this one down here. As you could see, it goes a little past 100, say 104 maybe. Coming from that direction, that will be 100 and 104. Now let's measure this angle over here. We got that one as 104. Let's measure this one over here. From beginning from there, as you can see, that's 90, that's 100, past 100 a little bit. Coming from this direction, 100, 1, 2, 3, 4. So this is 104 down here. That's 104 there. But if we take another point here on this alternate segment, that will also be equal to this. And of course, another point here, that will also be equal to this. But you know, for another reason now that we have that one, those three are equal to each other because they are all angles on this same arc on this same chord. So the angle between a tangent to a circle and a chord through the point of contact is equal to the angle in the alternate segment. If we take the other side, if we ignore this side now, and that angle, and we take an angle here, and we consider this angle on the alternate segment, then those two angles are equal to each other. So the angle between a tangent to a circle and a chord through the point of contact is equal to the angle in the alternate segment. As I said, this is about the most difficult of the 9 circle theorems that you have to learn. The next one is, a tangent of a circle is perpendicular to the radius or diameter of that circle at the point of contact. This one is fairly simple. If you have a circle and you have a tangent here, x, y, and then from the center of the circle, you draw a line to this point of contact, a radius, then what it is saying is this radius will form a right angle with that tangent. A tangent of a circle is perpendicular to the radius or diameter of the circle at the point of contact. Whether it's radius or diameter, the tangent and the radius or the diameter will be at right angles to each other, 90 degrees. 90 degrees, as you see here. A tangent of a circle is perpendicular to the radius or diameter of the circle at the point of contact. The tangent is perpendicular to that radius, or the radius is perpendicular to the tangent. So we just looked at those 2 more. So we have finished those 7. Now we have these last 2 to consider. The lengths of 2 tangents from an external point to the points of contact on a circle are equal. This is extremely simple. So you have an external point here, P. You have 2 tangents to that circle, and that tangent there touches that circle at B, and this tangent touches this circle at A. What it is saying is that AP and BP are equal to each other. Let's measure it from here to there. Let's see that a little closer. Looks like, what is it? 10.3 centimeters. Let's consider the next tangent, this one here. We measure that. See it a little closer? Yes, looks like 10.3 as well. So the lengths of two tangents from an external point to the points of contact on the circle are equal. And finally, this one is simple as well. The line joining the center of a circle to the midpoint of a chord is perpendicular to the chord. So let us consider this chord over here, BD. And we know that this is the midpoint. There is a midpoint. That is to say, this side here is equal to this side down here. If we draw a line from the center to that midpoint, that line will be perpendicular to the chord. This line will be perpendicular to that chord. We will get a right angle here. If we take that chord and we bisect it, this is the perpendicular bisector. You don't have to measure it to find out what it is. That is to say, if this side is equal to that side, when you bisect that AB, then this line is perpendicular. We can measure it to verify that. As you can see, it is perpendicular. We bisected this line here. So here would be the midpoint. So if this is the midpoint, it means that those two sides there are equal of that chord for that chord BD. If we draw a line from C to this midpoint, that line will be perpendicular to the chord. Conversely, the chord is perpendicular to that line provided these two are equal. So the line joining the center of a circle to the midpoint of a chord is perpendicular to the chord. So we just finished that. So as of now, we have completed all of that. This one is in yellow because that is the most difficult one to use. Now let's review briefly. There are the 9 theorem again. If you look at this, what does this apply to? Something about a diameter and a right angle at the circumference, which is this one. Let's look at this. Something about a cyclic quadrilateral and opposite angles being supplementary. Now this doesn't mean equal. Supplementary. That is this. Opposite angles of a cyclic quadrilateral are supplementary. How about this one? A chord or an arc down here that subtends angle on the remaining part of the circle. Angles at the circumference in the same segment of a circle and subtended by the same chord or arc are equal to each other. What about this one? You have a cyclic quadrilateral and an angle out here and an angle opposite there. So the exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. What about this one? Something about two tangents from a common point. That is this one. The lengths of two tangents from an external point to the points of contact on the circle are equal. And then this one. A line joining the center of a circle to the midpoint of a chord is perpendicular to the chord. That is this last one here. The line joining the center of a circle to the midpoint of a chord is perpendicular to the chord. And this one here about angle at the center of a circle and angle at the remaining part of the circumference, that's the very first one we did. The angle which an arc of a circle subtends at the center of a circle is twice the angle it subtends at the point on the remaining, at any point on the remaining part of the circumference. And this is the difficult one I told you about. The angle between a tangent to a circle and a chord through the point of contact is equal to the angle in the alternate segment. So this angle here is equal to that one in the alternate segment. So now let's quickly look at them. That one, this one, this one. They should bring back certain things to you. And then this one here, cyclic quadrilateral, opposite angles, cyclic quadrilateral, and this one here. These three. So that's a brief review of the 9 circle theorems we learned on this side. Some of them are easy, some of them are a little more difficult. So we did the review. We completed all of that so far. Now we will look at some practice questions. Now these practice questions are simpler than those in the actual CSEC exam, because those questions in the exam will also include other concepts in geometry not included in this objective. These are here to reinforce only the concepts learned in this objective. So here you have a diagram, and you know this angle is 50 degrees. What is that one, and that one? And you have to give your reasons. Now I have those 9 circle theorem here, and angle A is 50 degrees. Why? Because angles at the circumference in the same segment of a circle and subtended by the same arc are equal. So if you say this is 50 degrees, you have to give your reason. And the reason we have here is B. That is B over here. Now, what is angle B here? Or this angle at the center? It is 100 degrees. How do we know that? For this reason here. The angle which an arc of a circle subtends at the center of the circle is twice the angle it subtends at any point on the remaining part of the circumference. So if this is twice that and that is 50, then this must be 100. What about this one down here? It is 40 degrees. How do we know? It is at the base of isosceles triangle. Notice if that is a radius and this is a radius and this is a chord, then that triangle is an isosceles triangle because the radii are the same. And if that is 100, then these two angles here together would be 80. Divide 80 by 2 and you get 40. Let's consider this diagram here. We want to find D, E, and F in terms of a number. Now I have highlighted the theorem that we need to use on the right here. D. D is 90 degrees, and how do we know that? Because of this theorem here. The angle at the circumference subtended by the diameter is a right angle. See, this is a diameter, that, and this angle here is subtended at the circumference by that diameter, so it is 90 degrees. Now what is E? E is 90 degrees, and that 90 degrees is not related to this. And our reason is from this theorem, which talks about the line joining the center of the circle to the midpoint of a chord is perpendicular to that chord. So that's the midpoint of that chord. That's the midpoint because those two sides are equal. This is the center. This line here is perpendicular. That's our reason for that. Now we come to F. F is 90 degrees, and we have two reasons for that. First of all, reason G. A tangent of a circle is perpendicular to the radius or diameter of that circle at the point of contact. So that's the tangent. This is the radius. That must be 90 degrees. There is another reason, F, and this is a difficult theorem I told you about. The angle between a tangent to a circle and a chord through the point of contact is equal to the angle in the alternate segment. But remember, we got this as 90 degrees. This is that angle in this segment between that chord, which is the diameter, and we know this is 90 degrees. Therefore, that is also 90 degrees because this one is 90 degrees. But that is not the best way to do it. The shortest method you could find using just one of these circle theorem is best. Here we have another example. You know this angle here is 72 degrees. Find R and T. So these are the two theorems that we can use. R. Remember that theorem I was just talking about. This R here is 72 degrees. Why? Because the angle between a tangent to a circle and a chord through the point of contact is equal to the angle in the... So we know this angle. This angle here is in the alternate segment. So that is 72. And this one here, we can use that same reasoning. T is also 72 because of this same circle theorem. Or, now that you know that this one is 72, that one is also 72 because of this. Angles at the circumference in the same segment of a circle and subtended by the same arc or chord are equal. But you would use force principles first. If you could get that angle directly without going through this one, fine. If you cannot, then you will use this one to get to that. But we don't need to do that. We can go directly from this angle to that one. Lastly, this is a cyclic quadrilateral. You know these two angles here, 105, 100. Find those other three. I have indicated what two theorems we can use. Let's begin with P. P is 80 degrees. Why? For this. The opposite angles of a cyclic quadrilateral are supplementary. So if this one here is 100, that one is 80. And Q, for the same reason, is 75. This over here is 105. This over here must be 75. Opposite angles of a cyclic quadrilateral are supplementary. R now is 105. And we can use this circle theorem. The exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. Now you can do that, which is using first principles. However, you can also look at this one and say if this one is 75, then that one must be 105 because here they are supplementary. But remember what I said, to use first principle. If you could get your answer from this straight off without going through that third party there and getting to this angle, then that is the best, if you can do that. If you can't, then you will find this one and then use that one to find this one over here. So we just looked at some practice questions. As I said, these practice questions are simpler than those in the actual CSEC exam because those questions in the exam will also include other concepts in geometry not included in this objective. These that we just looked at are here just to reinforce the concept learned in this objective. So this is what we did here. Solve geometric problems using properties of circles and circle theorems. First of all, we look at the anatomy of the circle. And then we determine and justify, meaning give a reason for your answer, angles using the 9 listed circle theorems. And that brings us to the end of video 13 based on objective 6 in section 8.